Today's topic is the digital electronics first section, that the number system. The topic code is ELEC-DIGIE-S1. Before we move on to to discuss the number system, let's again review the difference between the analog and digital signal. The analog signal or analog system is defined as the physical quantities or signals which may vary continuously over a specified range. As the analog system, which consists of as defined as a continuous period over the period specified range. That signal is continuous. As you can see, 0 to 5 volt. This is also instantaneous voltage. Suppose one voltage signal, it could be current signal, anything else. So it is continuous. We have 0 to 5 means 1, 2, 3, 4, 5. It increases continuously. There is no discontinuity at all to maximum 5 volt. While digital system, the physical quantities or signals can assume only discrete values with great accuracy. This is a digital signal. You can see here discrete values. Here is the voltage is maximum volt 5 volt. This is a 0 line, or from here to here it is 0 volt. So two states are there, discrete values, either it is maximum or minimum, which is 0. There is no in between value. In between value does not exist. So we have two states in this case. So the digital signals, digital electronics is the branch of electronics in which we deal with the processing of the signals which have the two discrete states, which is the of maximum and minimum. We regard that states as a one state, the maximum, and the 0 state as the minimum. Okay, now we move on to the binary digital signal. Binary digital signal, how we explain that: an information variable represented by a physical quantity. Any information could be force, any signal, energy, or could be any kind of electrical signal or magnetic signal. For digital system, the variables takes only discrete values. The two levels are binary values, are the most prevalent values. Binary values are represented by abstractly by the two values 0 and 1s, where 0 is 1 bit and 1 is also 1 bit. Bit is the unit of that the particular value, the minimum or maximum value, whichever you take. Bit has been represented from the two parts of binary digit, that is bi is the form of binary and it is the digit from the digit. So it's a binary digit. 0 is a binary digit, 1 is a binary digit, and 0 is 1 bit while 1 is also a 1 bit. Words like these symbols are also used for these two states of the binary signal. For the binary signal is a false F and true T. False for the could be positive logic if you use, then it is the minimum value, and true is the maximum value. And similarly, low and high, that's L. Low means for 0 and high means 1 or maximum 5 volt or whatever you give that particular value. And words like on and off, switch could be in on state and off state. Off is the positive logic, is a lower value, on is a higher value. So binary values are represented by the values or ranges of values of physical quantities. So this is a logic 1 in positive logic. We take logic 1 is the maximum, logic 0 is the minimum. Okay, now we move to the number system. A number system, in case the decimal we human deal with the decimal number system. Our number system consists of total 10 numbers from 0 to 9. The total 0 is also a number, so if you count these, they are total 10. Now this is called base or the radix. 10 digits are used. The base of our number system is 10. 10 numbers we use: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Our radix 10 is called the base or the radix. So we will use the same analogy to describe the other number system, like from the whatever we are describing it in the decimal number system. So let's say, take an example, a number which is 512.74. 0.74 is a fraction part, and it is in the base. 10 means the decimal number system. So what we have, the it is actually nothing but it is a series of the powers of 10. Okay, so multiplied by its coefficient number, which is the, we can see here, this is series b raised to power 0 base, whatever this is, we are generalizing it for any number system. So if we take the base, whatever the base is, base raised to a power 0 for the whole number we take here, this is the fraction part, then multiplied by the coefficient or the number, whichever the number in the number system we have got, unit, 10, 100, and we all the number. So then the base is for 1 into d1, base for 2 into d2. So in this case, let's see the 2, 10 raised to power, what we take, that the whole 10 raised to power 1, 2 into 10 raised to power 1. So b is the 10 raised to power 0 means 1 here, 10 raised to power, in the second case, 1, b is raised to power 1 means 10 raised to the power base is 10, 10 raised to power 1 is 10, and in the last, the b is 10 raised to power 2, which is 10 raised to power 2 is 100, and there the coefficient which is being multiplying with it is 2, so 2 into 1 is 2, 1 into 10 is 10, 5 into 100 is 500. Here we will put the numbers, d1, which is in this case is 2 into 10 to power 0, which is here, sorry, this is d0, 2 with d0, the coefficient is d0, 2 into 10 to power 0, which is 10 to power 0 is 1, so here 1, d1 is 1, 1 into 10 to power 1 is 1 into 10 is 10, and finally 5 number, which is 5 is into 10 to power 2, which is 100, 500, 512 is the, we add them together, so we get 512. Similarly, on the fractional part, what we have, on this side, we call this the most significant, this one 5 digit MSD, this is called 5 is called the most significant digit, while 2 is called the least significant digit. So here we have the on the other side is a series, you can see, of the base to the power from 0, 1, 2, 3, and so on and so forth, while on the other side we add the fractional part, base raised to power -1, -2, -3, and so on. We take the base and multiply it by the respective that is the coefficient. So in this case, let's say d1 is the d minus 1 is the coefficient, d minus 2 is the coefficient, two coefficients we have got. So here we got d minus 1 is 7, 7 into 10, base is 10, 10 to minus 1, which is 1 over 10, so 7 divided by 10 is 0.7. So this is 1 over 10, this is the 10 to power minus 1 means 0.1, and this is 7 into 0.1 is 0.7. Similarly, we have got 10 to power minus 2 is 0.01, which is 1 over 100, which is 0.01, 4 into 0.04. We add these together and we get 0.74. So that's how in decimal number system we proceed to build a number or have a number. Now similarly we can have octal number system. In octal number system we have got the base 8 numbers 0 to 7. We have got uh, weight is equal to base raised to power position. So weight of the number is described as a base and raised to power position. So here is the weight of the number, which is again the similar kind of we have the series of these powers of the base times the number, the coefficients. So we have got in this case if we have, now we would like to convert it, suppose this is a number 512.74 now in the octal number system. So what we will have, we will now put in the similar way the base raised to power 0 into 2, which is a coefficient, base raised to power 1 into 1, base raised to power 2 into 5. So if you take the square of the 8 is 64 multiplied by 5, and 8 into 1 is 8, 8 raised to power 0 is 1, so it's 2. If you add all these you will get 330, while on the other side we have got now 7 into 8 raised to minus 1, 4 into 8 raised to minus 2, means 1 over 8 square, 1 over 8, this is 1 over 8 square multiplied by 4. If you calculate that, you get 0.9375. So that is the how we express. This is the actually base 10, but this is the base 8. So the octal number system, we proceed the same analogy using as if we have a decimal number system. So magnitude sum of the digit x multiplied by the weight, formal notation that is given by this series of these each respective number with the sum in between. Now decimal to octal number conversion, how we make that conversion. What we do, suppose there is a 175 is a number, we want to convert it into 8. What we do, we repeatedly successively divide it by 8. So if we look for the number here, so what we have, unless we get here the remainder which is less than 8, we keep on dividing this number. Let's say 175 divided by the 8 is 21, so here we get 21 is still greater than 8, so we keep on dividing, and 21 divided by 8 is, then we don't wholly divide it by it, but whatever the remainder we have got. So let's say 8 2s are 16, 1 is carried 15, so 8 1s are 8. So here what we have here, we get the remainder. In this case, when we divide it, 8 2s are 16, remainder is 5. So we can't divide this one, so whatever the remainder we have got, 2 we put over here. So what we have got, A0, A1, A2, the coefficients is, these are the numbers. We will obviously mark them with the most significant to least significant as we did before. So this is the last one, which is the remainder one, is the most significant digit, and to the least significant, 257 into 8. That is the how we convert an decimal number to octal number system. Similarly, the fraction, if you have a fraction in the 0.3125 base 10, how we'll convert that into the octal number system. So what we do, we in this case multiply the fractional number repeatedly with 8 till we get the 0 at the end, in the fraction. So let's say we multiply this 0.3125 and we multiply, and that is we get the 2 point something, so remaining 2.5, which is now 2 is now the overflow. We call this is overflow. Whatever apart from the fraction is 2.5, so 2 is overflow, that is taken as a coefficient over here as a minus 1. So 0.5 is left, this 0.5 is again multiplied, what we get 4.0 exactly, so we don't have any further fraction left with that, so 4 is the overflow in this case. So 0.24 will be the number in the octal number system. We convert, that's how we converted the decimal number, fractional decimal number, into octal number system. Now we have the hexadecimal number system. Hexadecimal number system has the 16 digits, the 0 to 15 means here A, B, C, D are actually in the next slide we will show 0 to 9 they are 10, then 11, 12, 13, 14, 15 and 16. So what we as a whole 0 to 9 we when we call 0 to 9 is 10 we we can call this actually 10, 11, 12, 13, 14, 15. So F is 15 last one, but 0 is a number which is again so 15 plus 1 16. So 0 to 9 we have got 10 numbers so over there, but we mark actually don't mark this 11 because it's a 9, then 10, 11, 12, 13, 14, 15. So that's we will be marking accordingly in the order. So let's now take an example of a number which is the 2 in this case is the 256. Let's see number we have got, okay, 485.476, and we would like to now convert a number. Okay, let's see, we have a number now I1EF 0.747A. This is a number, a decimal, the hexadecimal number. Let me write. So here we have the hexadecimal 1E5.7A is a hexadecimal number. We want to convert it into decimal number. So what we have, we use the same analogy which we use for all the decimal and the octal number system. There is a base raised to power starting with the 0. So and the 16 raised to power 0 is 1. Okay, then base raised to power 1 which is 16 raised to power 1 is 16, then base raised to power 2 which is 16 into 16 to 56, and multiply with the respective, here we multiply with 5 into 1 into 16, 2 into 56. So if you multiply these and add them together you get 485 here. While on the other hand what we have, the 7 into 16 raised to power minus 1 over 16, then plus the a value is, if you go from here, this is 9, okay, this is 10, a value is 10. So we will placing the value of these numbers, e in this case what we have, we are converting it to, that is the relevant values into that the to the, so this 10 in this case is the corresponding value. Like here get here 14 was a respective value of e. Here we have 10, 11, 12, 13, 14. So 14 is the respective value of the e. So we multiplied 14 into 16 here, and here we get the 10 which is a value into 16 raised to power minus 2. So altogether if you calculate that we get 485.4765 for 1 e 5.7a to the base 16. So that's how we convert an hexadecimal number to a decimal number system. So let's see how we make, as again we just quick review. We make the from decimal to octal and decimal to hexa. We divide, suppose this time we take it 250 the number, we divide successively with 8. Here in this case we divide this 250 by 8, which is 31, remainder is 2, and 8 3 are 24, remainder is 372. So the most significant way to least significant way we move on. So we got 372 bracket 8, that is the octal number system, base 8 is equal to 250 to the base 10. Now similarly 250, if number is converted to the hexadecimal, so what we get the 16 ones are 16, you should 25 you have over there, because you can't go beyond 16 2s are 32. That's so remaining 16 5s are 80, then we are left, we get the 90. So 90 minus 80 is 10. So we are left, that's it, that's the end of it. 16 is greater than 10 and 10 is less than 16. So what we get, respective value of the 10 is a, respective value of 15 is f. So what we have converted fa to the base 16, which is equal to 250 to the base 10. Here I have again given the respective the values of the a and f you get. Okay, at the moment we stop over here. We will continue in the next talk. We continue this in the second section of this the number system. Thank you at the moment.